the most used parts of design. So whenever you want to design any system, memory, almost all digital systems will have some memory in it. And this is not only used in latch or actual memory that you will need, because as you guys have realized, some registers, what we'll see is basically we're now going to see how to stack up registers, how to make a memory from it, right? So when I say memory, right, you guys have read enough about memory, probably have read about digital systems, know what a memory means. So when I say what are the kinds of memories, what are the kinds of memories you've heard, or what are the broad classifications in terms of the types of memory that you've
RAM and ROM.
Volatile and non-volatile.
RAM and ROM? Okay, so or volatile and non-volatile. Okay, and when you say volatile, non-volatile, what does that mean?
The
What does
one that
volatility?
Volatile,
Volatile
does
means
not
power
retain its
supply.
contents.
No, but yes, but what does, so when you say something is non-volatile, say, what does not, it's non-volatile means what is it, what is it, what is the non-volatility part of it? What does that mean?
It retains.
Non-volatile memory, even if power goes away, it retains its
Right. So
contents.
so important thing is it retains contents when power goes away. Right. So remember when we think about digital design, right? Even though we draw a gate like this, implicit in this gate is a power supply. Right. If you look at it at a transistor level design, implicit in this gate is a power supply and is a ground. So whenever you think about any digital design, a digital design always has power supply and ground to it, and that is the one which is providing energy for this circuit to switch or for this output node to get the voltage and current, right? So remember, when we say ones and zeros in electronics, they are associated with currents and voltages. And so those currents and voltages, that power, the output power, is basically coming from the supply voltage that you have. And so when you say something is non-volatile, you're essentially saying that if I've say written 100 into this memory, and now if I pull the memory out, right, then as long whenever I reconnect this memory back and power up my circuit again, the memory will continue to have the value 100. So the other terms you would have heard for the same is this is known as a RAM, that is known as a ROM, right? So generally non-volatile memories, and again this is generic. So in reality, volatile and non-volatile are not referred to as RAM and ROM, but in this class, which is again simple first level class, we'll generally refer to non-volatile memories as ROMs or read-only memories. That is, as a user, you only have the flexibility of reading from the memory, whereas RAM is a random access memory. So when you say something is random access, it means that you can write anything you want into the memory, and you can read something back from the memory, right? So whenever you think about memory, and so for those who are interested, fundamentally the difference between how these two memories work is that a RAM memory is based off our simple SR latch or a back-to-back inverter. So this is the basic bit cell of a RAM, right? Whereas ROM, remember ROM is storing. So when you think about a non-volatile memory is storing a particular value. So when you say something is storing, it is storing it as a physical change in this device. So there is a physical change that happens in the semiconductor device, right? So if you think about a very basic flash drive, say for example, you think about a USB drive, right? Your USB drive has a flash chip inside, and the flash chip, it is a non-volatile memory in the sense that I can pull the chip out from my computer, so it has lost power because a USB chip will draw power from the USB port. USB port has a 5 volt supply, right? So when you plug in your USB stick into your computer, the power supply for that USB stick comes from the computer that you're plugged into, and then that starts your access circuitry and everything, so you can use that to read and write onto the USB. But the main memory in the USB is a flash memory. And so how a flash memory stores a 0 or 1 is it actually changes the conductivity of a particular material in the device. So inside the transistor, you end up storing either electrons or removing electrons from certain layers, and that ends up, and that is a physical change in the device, and that essentially stores it as a state. So you store with electrons, you may call it a 0; without electrons, you may call it a 1. So basically zeros and 1 are stored as physical changes in the transistor, as opposed to 0 and 1 in this kind of a circuit, which is stored as a voltage, right? So in a RAM, 0 or 1 is stored as a voltage at this node, for example, right? So when you think about memory again, there are two operations that you always have to worry about a memory, right? One is known as the read operation, and one is known as the write operation. So you would have heard me when I've spoken to you about latches, etc. I use sometimes the word I want to write a 1 or I want to write something into it. So whenever you think about a memory, you can think of it either as two operations. That is, you want to, the memory has some data and you want to read the data of the memory, or you want to use this memory as a stopgap where you want to store certain data and use it later in the life cycle of the product, right? So in that case, you use it as a place where you want to store some temporary data. So you have the process of writing. So you want to modify the memory, write a certain word into the memory, and then read it at a later time. So generally, if you look at any memory, you have to support two operations. One is a read operation and one is a write operation. So if you think about a random access memory, a random access memory supports infinite reads and infinite writes. So anytime I want to, I have the flexibility of reading and writing any number of times from this random access memory. Whereas if you think about a ROM allows you to write only once. So if you think about a ROM, you can write it only once. That is, you use, so that process of writing only once is known as programming the ROM. So what you're doing is it's essentially using, so there are different kinds of ROMs available in the market. Olden times, ROMs used to be electrically erasable ROMs, right? So we had ROMs which are made with, where you could shine light on the ROM and erase it, or use electrical currents. So you'd connect it to a specific board which had the same pins as your chip, and you use currents on those particular pins to program it. So in a ROM, you normally can write only once, whereas you can read any number of times. So because of the fact that it's a read-only memory, you program it, and once you program it, you can use it infinite number of times. Whereas in the case of a RAM, right, a RAM allows you to read and write any number of times you want into the memory, right? So generally, you'll see that if you know, again, when you go and pick, um, say in your digital design, right, when you were doing your design assignments, your registers, etc., form part of the RAM block, right, where you want temporary storage of data. That's where you'll use a RAM. Whereas when you want to write, say, a starter program, say you're designing a system which starts by itself, and once you plug it into a system, you want some initial um, operations to happen. You want to reset something, say, for example. So all those sequences can be put inside what is known as a ROM, right? So the ROM will run the initial startup sequence. So even if you look at your BIOS in your computer, right, the BIOS is a ROM. So that is where your initial load up programs, your startup programs are put in, and that will do the initial. So that initial startup program, you need to use it once. You don't need to run it. You don't need to change it every now and then. So hence it's a ROM which is programmed once, and then it is accessed every time you turn on the computer, and that sets up the first few instructions of the computer to reset everything, to give your startup program, and then you go into the regular operation. When you start using the computer for computation, then you begin to use the random access memory because you need fast access to data. So we'll also look at two other kinds of memories. One is known as PLA, or programmable logic array. And we look at another thing is programmable array logic. Again, these are very powerful chips. So again, these chips are not customized chips. So when you think about a digital system, you guys have you heard this word, ASIC? What does an ASIC mean? Anybody? You guys must have heard this, right? When you look at any hardware companies, when you go for internships or when you start looking for internships, a lot of hardware companies or design houses would say we design ASICs. Anybody know what an ASIC stands for?
Application specific IC.
Very good. So this is an application specific IC. So one of the reasons why semiconductors became popular and why miniaturization of electronics happened, and why it proliferated very quickly, was the ability to design ICs for whatever operation you want. So this was known as an application specific IC, right? So initially when electronics was prevalent, like in the 80s and all that, right, 70s and 80s, there were a lot of these kind of chips which are known as programmable PLAs or PALs. What they were are standard issues of chips which you bought from the market, and for your particular product or your particular problem, you programmed these into certain specific what do you say, um, patterns, so that they were then used for your application, right? So these chips are generic chips that are available in market. You bring it and you program them for your specific application. So what this allows you is basically you can design any combinatorial logic from this generic chip that you buy by using what are known as fuses. So there are electric fuses available inside this chip, which you either blow or let them remain. And with that, you can buy this chip from the market and program it once to make it into a combinatorial circuit you want. Right. So these are generic. So hence these tend to be very cheap. I mean, they're less than a cent. You can go buy it and use them any number of times in your chips. The drawback with these is, since this is generic, it's not specifically optimized for application. So it may not give you the fastest speed. It may not give you, it might use a lot of, takes a lot of area on your board, for example, because for some simple operation, you might need a PLA. But then if you use a PLA, it's a generic chip. So you have to use a separate memory chip, you have to use a separate processor chip. So, you have to bring everything, signals onto the board, take it off the board, etc. Whereas in an ASIC, what you can do is ASIC gives you the power to put all this together into one single chip. We also have things known as, what does this mean?
System on chip.
System on chip. So system on chip means you further integrate components. So remember, whatever you had on the board, say 20 years earlier, what your parents worked on, that board have essentially been made into a simple chip, right? So a system on chip basically integrates not just processor, may integrate sensors into it, may integrate analog parts into it, may integrate memory into it. So as you integrate more and more items onto your chip, life becomes, you're optimizing it more and more, so you can get your application specific IC, which means it increases your profits because your chip is performing the best for your application. And so it would be the leader in its market segment, which means you can command a premium price on it, and which means that you can make profit, right? So that's generally how companies moved from using generic products towards ASICs, towards system on chips, etc. But nevertheless, we look at these because these are simple things to do simple problems in your undergraduate level or for hobbies or something. Like these are great things to do. And I'll introduce to you a very important class of chips known as FPGAs, or field programmable gate arrays. Again, these are chips which are normally used. Suppose you're thinking upon of a specific product, right? Suppose you want to design, say, a next generation gaming chip, right, which has very certain complicated algorithms that you're implementing on silicon. So when you have to do that implementation on silicon, normally once you design your algorithms, when you design your architecture, the normal cycle is then you put everything on silicon, and then you send it, you run a test chip, you send it to your foundry. The foundry sends back a chip after 6 to 8 months. You test it, you reassess your design. By then your customer might have defined certain new requirements. You put them again into a test chip. So a product cycle when you're developing an ASIC or an SoC takes around 2 to 3 years for a normal product. What an FPGA does is an FPGA provides you a programmable, it's like a, what do you say, programmable board that you have with you. So you can load up your algorithms, you can load up your circuit using fuses. Again, this is electrical fuses are available on this chip, which allows you to simulate what you have done. So this is mostly used as a simulation, right? So this is a simulation that you can do of your real chip on silicon. So this uses the same components, you gates, etc. Only thing is this is a very big chip, so you can convert your design by blowing appropriate connections between these various components and simulate your SoC on the FPGA. So therefore FPGAs become very popular when you have to, say, do field experiments, right? For example, you have this new, as I said, you have a new gaming chip, or you have a new chip which says makes search faster. For example, suppose you're working on one of the Google chips or Facebook chips which want to make searches faster. So in that case, while you wait for this chip to come from TSMC, what you can do is you can set up an FPGA, right, and run your various tests on that and prove it to your customers that, okay, this indeed reduces my time by, say, from 1 microsecond to, say, 10 or 20 nanoseconds. So all those kinds of and then you can look at some early data, you can start looking at reliability issues, etc. So an FPGA is essentially used for that. An FPGA is used to provide some early look at field level data that is available. So that furthers your case for why an SoC might be needed. So eventually an FPGA works out to be a very expensive solution, because an FPGA is a very expensive chip. It's a large chip, it's a power hungry chip. So you cannot design a product of an FPGA. But what you can do is you can take the FPGA, go and test your design on it, confirm your field level analysis, and then come back and then do the same thing on the SoC. But learning from the field, you can implement a better SoC. So the FPGA is, as I said, a simulation platform available to you to simulate the hardware, if you will. It's not a software, it's actually simulating the circuit through a variety of electrical fuses that you have. Okay. So again, so we look at these different kinds of chips. Again, FPGA, I'm not going to go into programming and all that, but I'm going to give you an idea about what an FPGA looks like, what are its basic building blocks. So it's more of a information sharing that I will have with you. But I want you to keep that in mind. So as you go on, through your career in the next few semesters, you can figure out, okay, when somebody says go and do this on FPGA, what does it mean? What is the use? Because remember, FPGAs, by the way, the biggest player in the FPGA market today is Intel and Xilinx, right? And Xilinx is again under acquisition. I think AMD is planning to buy out Xilinx. So I think it's going to the top two companies. But you see that there's a lot of value in having a simulation worthy chip available. So FPGAs again are never, you'll never build a product on FPGA, but it is very useful when you're doing a design of a chip. So when you look at PLDs or PLAs, typically what these consists are nothing but a bunch of AND gates and a bunch of OR gates. So we'll look at this again in detail. So PLAs and PALs are used to basically implement any combinatorial function which can be written as an AND OR function or an OR AND. Remember, any Boolean function can be written as an AND or an OR AND, right? So using that logic, you can basically blow fuses and create any Boolean function on these chips. Okay, so this is kind of the rough topics that we'll cover in the next 2-3 classes when we deal with memory and programmable chips. Okay. So let's now talk a little bit about the first type, which is the random access memory. So whenever we talk about a memory, the basic memory unit is known as a bit cell, right? So whenever so as a device person, as a circuit person, if you want to improve memory, if you want to come up with the next generation memory, right, you will spend a lot of time analyzing what is known as the bit cell, or the smallest building block of the memory. What does a bit cell do? A bit cell can store a 0 or a 1. So it is a 1 bit storage element which can store a 0 or a 1. So again, remember, this is in our limited understanding of the world where we look at it as 0 or 1, right? If you guys want to go into quantum computing and all that, then you begin to see that they essentially don't look at the world as 0 or 1. And then when you start looking at entanglement and all that, things become different. Or even you can think of logic, instead of being 0 and 1, you can think about a 4-state logic, 8-state logic, etc., 6-state logic, right? Where instead of thinking of logic as just 0 and 1, you can think of logic consists of 3 basic states or 4 basic states. But the world today still thinks of logic as 0 or 1, so we'll keep our understanding limited to just that. So when you think about a bit cell is the basic building block of the memory, which can store a 0 or a 1, right? Then a next level of memory hierarchy, if you consider a group of bits is called as a word. So in memory, we normally talk about words. So when we say a memory, we store words in a memory, right? So remember, a word is the bigger unit of a bit cell. So bit cell has 1 bit in it. A word, so when I say a 1 byte word, right? What does a 1 byte word mean? How many bits will it have?
8.
8, right? So a 1 byte word essentially means that you will have 8 bits. And so 8 bit cells will be read together, and that whole data is called as a word. So why is word important? Because when we think of memory, we store data in the memory as a form in words. So generally, you'll see that not all memories give you access to individual bit cells. They will give you access to words. So when we think about storage in a memory, always remember we'll store it as words. So our smallest unit in the memory will be a word, not a bit. Okay. So now, what all generally a memory is used for? As I said, a memory can be used to store numbers, right? Can be used to store instructions. So when you guys will do microprocessors next semester, not instructors, instructions. When you do microprocessors next semester, you'll look at this in more detail. That you'll have this RAM, which is you'll keep pumping your instructions into it, and then it pulls off. So depending on what the queue is, it will pull off either the first and first or last and first or whatever. You have different ways of designing microprocessors. So many a times, if you want to perform say 5 or 6 processes one after the other, you can load them up in a memory, and then the memory can pop out instructions one at a time, and then that particular instruction gets executed, and then the next instruction. So uh, and how is this? And so along with the instructions in memory, you'll have a program counter. And the program counter will keep counting, or will keep pointing in computer science parlance. It will keep pointing to the next word in the memory, which corresponds to the next instruction. So you'll have a counter, digital counter, which has a digital output, right? And that will be essentially pointing to where in the instruction set am I looking at. So your memory will have a bunch of instructions. You'll have a program counter that is going to point to an instruction. So it will tell you, okay, this is the current instruction I'm working on. My next instruction is going to be so and so, right? So that's where you use memory. We also use memories, obviously, to store alphanumeric characters, right? So floating points, alphanumerics, all those will require memory. And as you guys know, if you want to store a simple integer, life is much simpler. When you want to go into alphanumerics, when you want to store floating points, you have to allot more and more bits to the word, or in other words, the word length keeps increasing, right? Word length also becomes, so again, especially in floating point, right? If you want to maintain certain accuracy, then you'll have to ensure that your word is large enough so that you get a particular accuracy. Again, if you're going to work in digital signal processing, if you're going to work in data processing, right, those things become important because there your word length becomes very large when you have a lot of calculations that you need to do on your chip. Okay. So when I talk about what is storage, when I say what is memory storage, generally I'm referring to is number of bytes it can store. Right. So when I say something is 1 kilobyte, how many bytes is it?
1024.
2 to the power of 10 bytes. And how many bits?
2 power 13.
Good. Right. Remember, 1 byte is 8 bits. Right. So again, 1 kilobyte is 2 power 10 bytes. And similarly, you can go into 1 megabyte, 1 terabyte, etc. So you guys know all this, nothing new. So now let's think about what is the top level block diagram of the memory. Right. So let's think about a memory unit. Let's see what should the top level diagram be. So let's assume this is my memory unit I want to define, right? And so the memory unit, let's assume it has 2 to the power of k words that you can store, and each word is made up of n bits, right? So again, when you think about the memory, you want to think about how the memory is designed or how is it organized, right? So when I say how is a memory organized, I'm talking about how many words can it store and how many bits per word, right? So when you think about now, when you think about the top level diagram of this memory, you basically need to have an input port of n bits. So this would be your data in, right? So every time I want to write something into the memory, it needs to be a word that is n bits long. And if I want to write in, I have to write that into my data in port, right? So if you think about it, it's basically n lines coming into this memory unit. Similarly, going out, I'll have a data out, which will be n bits long, right? Again, this n number justifies how many inputs I can take in parallel at a time and how many outputs I can give out in parallel. In addition, for every word, I need to have a unique identifier, right? Because what I want is that suppose I have 3 words stored in the memory, I should be able to access all the 3 words, right? So which means that if I have 2 par k words, how many bits do I need to access these 2 par k words, or how many how many bits do I need to access 2 par k words?
n into 2 power k.
No, wait. How many bits do no, sorry, I didn't mean bits. Suppose I want to access every word, right? So I want to access 2 par k words. How many lines will I need to individually access 2
K
par
line.
k?
K line.
K lines, right? Every, so you can think about every minterm can be associated with a particular word, right? So I'm calling these k lines as my k address lines, because I'm saying that every, so this will have k bits. So these address lines, so this is your address. So every combination of k will point to a unique word in your memory unit, right? So you have k address lines, and k address lines will allow you to access every individual word in this memory, right? And then you'll have, as I said, you want to do 2 operations. So you need to have 2 inputs, a read input and a write input, to tell the memory what is it that you need to do. So if I think about the top level block diagram of this memory unit, right? I have k address lines, I have n data input lines, I have n data output lines. In addition to the address lines, I have a read or a write. And then again, if you guys are smart designers, you will always include an enable in it, right? So I will say that I will ensure that this memory unit doesn't turn on when I don't need to, and I will enable or I will supply it power only when I need to access this memory. So normally I'll use a memory enable for it. So if you think about again, so always remember k address lines or 2 par k words, right? And so because you want to access each and every point in the memory. So you can also think about it the other way sometimes, which helps to think about memory, is that you can call these, 0, 1, 2, etc., etc., all the way to 2 power k, right? And everything has, right? So 0 or 1, 2, and -1, right? So that's how your memory is
Excuse me,
addressed.
sir.
Yeah.
Sir, can you explain the read and write part again?
Right. So remember, what are the two things I want to do in the memory? If I look at the random access memory, I want to be enabled. I need to know how to read into it or how to write into it, right? So what I'm saying is, if I want to design this top level unit of the memory, I need to have two signals which tell the memory unit whether I'm reading into it or I'm writing into it, right? Because if I'm reading from the memory, right, then I don't have to see what is on data in. When I'm reading to the memory, what am I doing? I'm going to give it an address and I'm going to expect some data in the output, right? There I don't have to consider what's happening in data in. Whereas when I'm writing into the memory, what am I going to do? For writing, I need to have an address and I need to have a data in. So once those two are available, once I then say, okay, write into it, then it will, whatever is on this data input is going to be written into the memory with the address as to par as pointing to this k, to the min term of k, right? So this read and write are basically I'm using this to identify if I'm reading into the memory or reading from a memory or writing into the memory. You can ask me, can I use the same signal where I say read slash write? I say read or not read, right? Yes, you can do that because there are two operations. You can use a select line, one select line, which says that if it is 0, it is read. If it is 1, it is a write. So you can use that also. But general design is that we keep two separate inputs, which are read and write. So in this case, when that line goes high, that is when this read line goes high, it indicates to the memory that I'm reading from the memory. When this write line goes high, it indicates to the memory that I'm writing to this memory. So I will also ensure as a user that read and write both don't go high at the same time. Or I can design this memory in such a way that if read and write go high, I can say read always has priority. So if read or write go high, then I'll say that in that case, read will also always assume priority. That way I don't damage anything that's inside the memory. But if I say read always has priority, then that means that you can also modify the content of the memory, right? Because you're modifying the content of the memory. Clear?
Yes, sir.
So suppose I have an address line which is 10 bits long. How many bytes of memory can I use?
2 to the power 30,
Number of bytes.
2 to the power 10.
Yes, good, right? So if my address line is 10 bits long, then I know I can access 1024 individual combinations of the address lines, right? So I can store up to 120 1024 bytes. Is that clear? So the address line tells you how long this memory is. And now if I say that each word, so in this I can say that if each word is 1 byte long, then you can say that, okay, the memory size is 2 power 13 bits, right? But if I say each word is say 4 bytes long, right, then this increases to 2 power 15, right, bits. So this tells me that how you're organizing the memory again. So address lines is one thing and the number of bits per word is the other thing, right? Again, what I want you to remember is that addressing is happening at the word level, not at the bit level, right? So which means that you cannot access half a word. You cannot access the nth, the jth bit of the word normally. If you want to do that, you pull out the entire word out and then you can use a multiplexer or something like that to pick out a particular bit in that particular word. But generally when you use a memory in design, we always worry about it taking inputs n bits at a time and giving outputs n bits at a time. Okay. So now let's think about the algorithm. Now suppose I say that I want to read the memory, right? Suppose I want to read a memory. What should my algorithm be for that? Anybody want to tell me? Let's write out the algorithm. Suppose I want to read from the memory. How should I play around with the signals? What should my signals be like?
So can we have a pointer that initially points to 0 and
Hmm.
it moves to the next word and it decrements the address line input by 1 and it keeps on
Hmm.
going until it reaches 0 and then we arrive at the
Right,
word.
but that's because you want to address all the words. So initially, what you can do is, so let's think about. Suppose let's see how do I read this. So to read, what do I need to do? First thing I need to do is apply the address onto the address lines, right? So suppose I want to read the fourth word in the memory, then I'll apply the corresponding address to that address line. So the first thing I want to do is, before I read anything, I need to ensure that the address has appeared on this address line, right? Otherwise, there's no point in turning on this memory. So I will first ensure that the address is ready at this point. Once the address is ready, then I will enable the read signal, right? So let's assume that once the address is ready onto this address line, then I enable the read.
Can we use a decoder here?
Yeah, we were going to talk about that. Just hold on. Yeah, we will use decoders. Right? So once I enable the read, right? So now what happens is once you have the address line available, once the read is enabled, then you know it is going to take some process time and then data is going to be available on the data out port, right? So if you think about this, once these two, so first you ensure that the address has settled down. Now look at the words I'm using, right? Remember, these are all sequential circuits. So you need to ensure that you have given sufficient time for the address to settle down before you enable read. You don't want the address line to change while the process of reading is happening, right? So again, remember, go back to the concepts of setup time, hold time in the flip-flop, right? Same thing. You want this address line to settle down to its value before you enable the read. And once the read is enabled, you don't want this address line to change. You want this address line to remain a constant during the read process. It will take some finite combinatorial time once the read signal is given for the data to appear at data out, right? So again, so if I want to find out, if I want to get the data, once I've enabled the read, I should not immediately go and pull the data from data out, right? Once I've enabled read, I will ensure that data out has transitioned completely before I start reading from that particular port, right? So remember, the order, the sequence of events become important. So once you enable the read, then once output settles, you can pick the output word from the data outlines, right? So again, a flip-flop is a good proxy for how a memory works. That is, you want, because eventually all these are going to be made up of flip-flops, right? So what you essentially want to think about is that your address should be settled completely, then enable read. Then, so now let's use the same logic. Suppose you want to write to memory. What would be the algorithm? How would you write to a memory?
First, we'll apply whatever we want to write, and then we'll enable write,
Hmm.
and then it will get written to some register.
But how do I find out which register you want to write it to?
Oh, we'll also need to specify the
So
address.
first, I think you should.
So same logic. First thing is apply address. So again, normally what we do is we first go in and apply the address onto the address lines. That is where we want to write. So this is nothing but where do you want to write the word? Once you've done that, then you enable, then again, what you want to do before you enable write is you want to ensure you apply the data to data in. So you want to ensure that this port has the address ready, this port has the input word ready before you enable this unit, right? Again, because you don't want these 2 points to change once the write is enabled, because write is again will take a finite time. So during that time, as the gates transition, you don't want these inputs to transition. So again, before writing, you want to ensure that your final address is ready and available at this port. You want to make sure that the input data is ready and available at this port. Once both these ports have settled down, then you apply a write, and then you write whatever is data in into the particular point, right? So again, here the logic would be that you initially, after you apply the address, you apply the data to data in, right? And then you enable write. And once you enable write, basically that address will be written to that particular, the data will be written to that particular address that you have. Again, remember, once you've enabled write, once the data writing process is complete, you have to then disable write. You cannot keep write on at all the time, right? Keeping read on at all the time is also not recommended, but enabling write, you have to be very careful about it. You want to enable write just for as long as it takes to write or to transfer whatever is on this input port into the memory. But once you're completely sure that what's on this input port has been transferred to the memory, you want to ensure that you bring the write down again, because that way you can keep this unit isolated if there are any changes happening here, right? So these signals become very critical, and these are timing sensitive signals. So this is where, when we discuss timing diagrams, when we discuss timings, those become important. That is, you essentially want to always ensure that the write is a pulse. Write should never be enabled and left it as is, right? Write should always be a pulse, and the write should be the time for the pulse width will be determined by the worst or the longest time taken for data to be written into the memory. So now, physically, if you think about it, again, this is second order effects which are not expected from you in this class, but when you think about it, this in reality, this memory unit is spread on a finite area of a chip, right? So which means that if your data inputs are coming from the top, writing something which is close enough to the data input port will require less time than writing something far away from that data port, because these signals have to travel over metal wires, right? They are interconnects, there are transistors as they travel through. So writing something far away from the data port maybe it may take longer than writing something here. So the total time this write has to be high really depends on what is the worst case time required for this memory to write from data into the memory, right? So again, what I'm giving you is very, very simplistic view of memory. In reality, all these, a lot of tests need to be done for you to figure out what is the worst case write time. Like what is the pulse width I need to ensure write has, so that anytime I given a data input word, it is written reliably into the memory, right? So that you need to understand what the worst case is, and you need to plan for that whenever you want to write or read into the memory. So as I suggested, so one way to think about these signals, other way would be that, so you can also think of this as one enable signal. So suppose I think of my memory. Suppose I think of a signal read comma write or read slash write, right? And I can call this read bar slash write, and I'll talk about another signal, say an enable signal. So I can also design access memory like that. I can say, let's call this signal enable. Let's call this read write signal. I mean, by doing this, I've already given you the logic, right? So what does this mean? This means that when this is 0, I don't care what's on this signal, the memory is disabled. That is, the memory is impervious to what's happening on its output or input ports. When I want this to read, then I will ensure that enable is set to a high, read is set to a 0, right? Sorry, sorry. I'm going to follow your textbook convention. Let's call this, right? So when this port goes to 0, it says write to the selected word, and this is because I assume that the address is available on the address line. So when address is available on address lines, so before I do all this, I will ensure that address is ready. In the case of write, I will ensure that the data is ready at the input, and then I will push enable to high, and I will push read write to 0. And in this case, then I will be able to write into this. And if I want to read again, I do this combination of 1 1. So this would then read as read from the selected word, right? So you can also think about enabling or using a memory like this, where you essentially use two control signals, an enable signal and a read write bar signal. And the read write bar, again, the convention for this port is going to be read write bar, which tells you that it will write into this memory when this port is a 0, and it will read from this memory when this port is a 1, right? So let's think about, suppose I ask you, I'll stop here. Let's think about a timing diagram for a write operation. So always remember there's a clock. And let's just number these clock pulses. Say I'm sure I can write any word into this memory within 3 clock cycles. I've budgeted a write operation will take only 3 clock cycles, right? So what I would do in this case is, at the start of T1, I will ensure that so if I look at my address, ensure that my address is valid throughout this entire period of writing. So again, you guys have done Verilog to know that these indicate that signal transitions, right? So this point, I'm saying this address is valid on the address lines. So when address is valid, and then what I'm going to do is I'm going to enable the memory. And when I disable them, let's assume that I have to generate a timing signal, right? So normally, I'm showing you what a typical timing diagram would look for an write process. So I would say memory enable, I will give it a high during this process. At the same time, I will give a low on the read write bar signal. Right? And if I look at the data output, right? So remember this, so at the start of T1, I will ensure that address is valid. So whatever setup time needs to be done, I need to ensure that I don't violate any setup time. So address should be valid before T1, right? Once this has happened, I will also enable my memory, and I will also enable my read write. So once that happens, then the question is, some point after this, my data is going to become valid. So if I look at my data out will become valid at some point after my read write signal has gone down, and this is going to be my data valid. Sorry, I'm doing data right. No, sorry, my mistake. This is data in. So let me, sorry. So data in also should be ready before my read write has gone down, right? So in this case, what I will do is I will ensure that my data in is also ready like my address. So data should be valid So what I'm trying to say is that when you want to design a write operation, you will, this is the only clock available to you, right? So once this clock is available to you, based on this clock, you have to generate these signals, memory enable, read write bar signals. You need to ensure that your address and data valid are ready before T1. So these are the two timing signals which you need to generate. So this is where timing signal generation becomes important. So we have special circuits to generate these signals. So these signals are going to be generated for specific times which you will need to design. So if I give you a clock like this, you should be able to design a state machine which can give you a memory enabled signal like this, right? I mean, it's simple to do this kind of a design. So you can then figure, so that is essentially what the digital designer does here, is that he or she figures out what are the timing signals required, generate these timing signals. Once these timing signals are generated, then these can be used to control data flow in and out of the memory. Okay. So what I'll do is we'll stop here because of way over time, and then we'll continue on Wednesday. Right. Okay. Thank you.
Sir, we can model RAM as like one K to 2 raised to K decoder and 2 raised to K parallel
Yes, that's how we are
flow.
going to model. That's how we are going to design. That's how a RAM is designed.
Okay,
So when I teach you the organization of RAM, that's what we're going to use.